ascensores in Chile are cable cars built on stilts. As the figure shows, one car ascends as the other descends. Cars use a two-cable arrangement to compensate for friction. One cable passing around a large pulley connects the cars. The second is pulled by a small motor. Suppose the mass of each car is 1,500 kilograms. Coefficient of rolling friction is 0.020, and the cars move at constant speed. What is the tension in A, the connecting cable, and B, the cable to the motor? So the first thing that's going to be important to solve this problem is just recognizing that because of the constant speed, the cable cars are going to be in dynamic equilibrium, which means that if you add up the forces acting on one of the individual cars, those forces are going to be equal to 0. So knowing that, you can go ahead and make a free body diagram of, in this case, since it's A is acting about the connecting cable, I made a free body diagram of cable car A, as it's not experiencing that tension from the cable to the motor. So this was probably the trickiest part, is just making this free body diagram and making sure all the forces are pointed in the correct direction, and also recognizing that you can tilt the axis to make this problem much easier. It makes it so you only have to break mg into its individual components. And those individual components of mg are going to be mg sine theta in the I direction and mg cosine theta in the j direction. So that's going to be important for later on. But you can see that theta is going to equal 35 degrees. So yeah, as I said, that'll be important later on. So we do know that we can set those components equal to 0. And in this case, I'm just using the components in the I direction because that's where the tension is, which means that we only are going to have to account for, as I said, that I component of the force from gravity. And so if you set those equal to 0 and then solve for tension, that's going to be tension equals the force of gravity minus the force of friction. So as long as we can solve for those two individual forces, we'll be able to solve for tension. So you can see here that we can. The force of friction is that rolling coefficient of friction times mg cosine theta. And that mg cosine theta correlates with that j component of gravity, as in this case, since we're in equilibrium, that those vertical components, normal force and j component of gravity, are going to have to be equivalent. So that's where that comes from. So if you plug in numbers there, it's going to be 240.83 newtons. And then the the I component of the force of gravity is just mg sine theta, which, as I just reminding you, that the problem gave us that theta is 35 degrees. And when you solve for that, it comes out as 8,431.6 newtons. So you just plug those in to the an equation that indicates that tension equals force of gravity minus force of friction, and the tension comes out as being 8,191 newtons. So that's the answer for part A. So part B is asking about the tension in the cable to the motor. So I drew a new free body diagram for this, a free body diagram of cable car B, and the forces look slightly different on this one, with the tension from the motor and the tension from the cable car in the positive I direction and the force friction in the negative I direction. Normal force and mg look more or less the same though. So we can basically use the same concept that we used in part A in order to solve for this. That concept of because the car being in dynamic equilibrium, adding the forces together will equal 0. Allowing us to solve for an individual force. So when we do that, we get that the tension of the motor is equal to the I component of the force of gravity plus the force of friction minus tension. And we already solved for all of those numbers in the previous part. And since the cable cars have equivalent masses, they both equal 1,500 kilograms, we can use the same numbers that we previously solved for. So for part B, the tension of the motor comes out as being 481.4 newtons. So yeah, that's the answers to part B. Thank you for listening.